Okay, so starting with number 7, I like to give you an equation that you recognize so that we can compare the calculus answers to the answers that you know to be true. And when you do that, then you can start trusting the calculus on its own. So for example 7, we have a little circle right here, x squared plus y squared equals 4. This circle is centered at the origin. The center is at 0, 0, and the radius is equal to, what do y'all know? About 2, right. Because the standard form for a circle is x minus h squared plus y minus k squared equals r squared. And in general, the center is at h comma k, and the radius is equal to r. So since we don't have the plus or minus anything, the center's at the origin, and the radius is 2. So let's come over here and sketch the graph. I'll use brown for the axes. And then all you have to do from the center is go out 2 units in either direction. And we'll put a little solid dot there. And then we just connect them with circular arcs. Something like that. All right, so that's actually part A. That's what it asks us to do. Part A, sketch the graph. There it is. Here's the x-axis. Here's the y-axis. Beautiful. Okay, part A2. Another part A. Find dy dx. All right, so dy dx. Remember, if it's not solved for y, your first consideration is, do you want to solve it for y? This one is actually pretty easy to solve for y. But because it's y squared, when you solve for y, it's going to be y equals plus or minus, which means it's going to be 2 different functions. It's going to be the top version that opens up and the negative version that opens down. Do you want to be in charge of 2 different equations and have to know when to use each one? Heck no, especially when there's a way to get by with just one equation. We know how to find dy dx implicitly, so that's what we're going to do. So here we go. d dx of the left side, x squared plus y squared, equals the derivative with respect to x of the right side, which is 4. All right, so here we go. On the left, we get 2x dx dx, which is 1. We don't write it, plus 2y dy dx, which we do write. And the derivative of any constant with respect to any variable is 0. Constants don't change, no matter who's asking them. Now the algebra does, I almost said dissolving for dy dx instead of solving for. You bring the 2x across, it becomes negative. You divide through by 2y, and you end up with negative x over y. If you need to show more steps in the algebra, feel free. So notice the derivative is a pretty easy little ratio, but once again, it does require both the input for x and y because our graph is not a function of x. It doesn't pass the vertical line test. All right, step B, using calculus, verify the horizontal tangents. All right, so let's come over to our graph that we did on part A, and I'll use red. Horizontal tangent line, let's see, there's going to be, let me copy that. There's going to be one at 0, 2, and one at 0, negative 2. So, oops, we don't need the calculus to find them. In this case, because we recognize the graph, we can get them that way. But we're not always going to be able to recognize the function and the graph of the function, or the equation, I should say. So what we're going to do is make sure now with the calculus that we get the same answers. And if we don't, then something's wrong, probably with the math. So to do that, dy dx, here's what you're going to show. Let me choose, I'll stay with red because we're doing horizontal tangent line. The derivative is negative x over y. To solve for horizontal tangents, it's going to be when the derivative is equal to 0. And you always want to show the equation you're solving. But because it's a ratio, you're going to want to probably say not just equals 0, but equals 0 over non-zero. Because it's a ratio, it's only going to be a horizontal tangent if only the numerator is equal to 0. So by saying that, you're going to earn a check. That's going to show the equation you're solving. Now we'll take the numerator, and I'll just associate the negative with the x on the top. I'll just take the numerator, negative x, and set it equal to 0. Take the numerator, set it equal to 0, and now solve, and you get x equals 0. Now that you have x equals 0, you can plug it back in to your original equation, which was x squared plus y squared equals 4. So, plugging in a 0, we get 0 squared plus y squared equals 4. And if you solve for y, you get plus or minus 2. And so now you can answer the question. We have horizontal tangents at the following points: 0, comma, negative 2, and 0, comma, positive 2. Is that consistent with what we knew to be true? Bless you. Yeah. Yeah. Exactly what we knew they were going to be. So the calculus worked. Way to go, calculus. Way to go. Pretty impressive that you knew that without knowing what the graph looked like. All right, part C. Let's choose green here. Using calculus, verify where the vertical tangents are. So coming over here, if you draw a little vertical line, and let me copy and paste that one. We have a vertical tangent over here, looks at negative 2, 0, and this one looks like 2, 0. Again, we can answer the calculus question without any calculus because we know what the graph looks like. Let's see if the calculus can get that just by using the algebra involved. So dy dx is negative x over y. If you're trying to find where the graph has vertical tangents, a vertical tangent line has infinite slope. And infinite slopes come from the derivative being non-zero over 0. Remember from the other day, if you get 0 over 0, the derivative doesn't exist, but for a different reason. Not because it's infinite, but because it flat out doesn't exist. In this case, we want a very specific DNE. We want the derivative to be non-zero over 0. That's infinity. So once you do that, you'll get a check for your setup. Now you're just going to be setting the denominator equal to 0. And since I let the negative be part of the numerator, the denominator for me is just y. Well, there's never been an easier equation to solve for. Y equals 0 is already solved for. So when you plug it back into your original x squared plus y squared equals 4, you get x squared plus 0 squared equals 4, and you solve for x and you get plus or minus 2. So we have vertical tangents at the points negative 2, 0, and 2, comma 0. And once again, the calculus impressed us. It got the right answers. All right, now a little follow-up question here. Part D. At what value or values is the slope of the graph 3 over 4? Well, 3 over 4 is not horizontal, nor is it vertical. Let's see what it looks like. I'll use, let's use brown. 3 over 4 is probably going to be somewhere right around here. It's going to be a little bit past the halfway point, where it's a little shallower. Now, if we have one solution up there, it looks like there'll be kind of a symmetric solution down here on the bottom, somewhere in there. And I just need to find those values. So here's what we do. If we want to know where the slope is 3/4, we're going to take the derivative, dy dx, and we're going to set it equal to 3/4. That would earn you a check right there, just for setting it equal to 3/4. But of course, in this case, we probably want to set the other version of the derivative equal to 3/4, namely the negative x over y piece. Now, in this case, can we just go straight across and say, let x equal negative 3 and y equals 4? No, because x may not be 3 and 4. There are infinitely many ways to get 3/4 from a ratio, right? 3/4 could actually be 6/8, or it could be 4.5 over 6, right? So we can't just assume that x is 3 and y is 4. But because we now have one equation with two unknowns, we can't solve it as it is uniquely for a single solution. So whenever you set your derivative equal to something and you still have two unknowns, what you're going to do is you're going to solve for either variable. It's going to be kind of like a substitution from Algebra 2. It doesn't matter which one you solve for. If you multiply both sides by negative y, you'll get negative 3/4 y. Or you could say y equals negative 4/3 x. It doesn't really matter. Just solve for one of the variables. Now what you're going to do is you're going to take that equation and you're going to plug it back in to your original equation of the circle. or the equation of whatever it is. So what that's going to allow you to do now is it gives you the necessary conditions of y, or of x in terms of y, where you'll have a slope of 3/4. And you plug it in now, and you get negative 3/4 y quantity squared plus y squared equals 4. And now you have the equation in terms of a single variable. So now you're going to have a unique solution. You simplify, and you get 9/16 y squared plus, that's really a 1y squared, equals 4. Excuse me. So what's 9/16 plus 1? 25/16. Yeah. Y squared equals 4. A little bit of algebra now. Multiply both sides by the reciprocal. You get 4 times 16 over 25. And when you take the square root of both sides now, you consider plus or minus. So you can either call 4 times 16 64, and then say its square root is 8. Or because 4 and 16 are perfect squares themselves, it's the square root of 4, which is 2. The square root of 16 is 4. 4 times 2 is 8. And the square root of 25 is 5. So what that does is it gives you the two y values now where the slope was 3/4. So here are the actual solutions. X comma positive 8/5 and x comma negative 8/5. How are we going to figure out the x values that go with them? Plug them in. Now you actually have two places you could plug them in. You could take those two y values and you can plug them in right up here to the original equation of the circle. That's one way to relate x to y. Or in this case, you could also plug them in to x equals negative 3/4 y. Of course, that one's going to be a lot easier, right? So that's why I boxed it. Just like we would if we were doing substitution, you want to plug them into the easier one. So when I plug in a positive 8/5 for y, the 8/4 is going to become a 2, and I end up with negative 6/5. Oops. Wrote with a highlighter again. Negative 6/5. If you plug that 8/5 in for here. And if you plug in a negative 8/5 for y, you're going to get positive 6/5 as an answer. And there you go. That's like negative 1.2 and 1.6. Negative 1.2, 1.6. Let's see. Negative 1.2, 1.6. Perfect. That's perfect. Of course, my graph was not perfect, but the coordinates that the calculus gave us were perfect. Negative x positive y, positive x negative y. That's what we got. All right, so what we just did here, taking our equation and solving it for one variable, this is actually going to be more common than not. What we did in part A and B is when I set the numerator and denominator equal to 0, I already had a single variable, and so I got a unique x and y value there. But what typically happens with these is you're going to have two variables here, and you're going to have to solve one in terms of the other and plug into the original. Now, before we go on to example 8, I want to show you another thing we could do here. I claim that there's a quick and easy way to come up with the calculus derivative equation, dy dx equals negative x over y, without using calculus. That is, without taking the derivative implicitly. Would you believe me, or would you like to see how that's done? Okay, good. Curious learners of calculus, you? No, it's actually pretty nifty. Let me just get rid of all this clutter. And let's say that I'm interested in finding the slope of the tangent line. I'll just draw a tangent line in green. Right there. I'm going to call that point of tangency x comma y. So that's just going to be some random point on the graph of the circle that satisfies the equation of the circle, okay? Let me come back and draw that later, because my circle's not perfectly round. Here's the center of the circle at 0, 0. If I draw a line connecting the center of the circle with the point on the outside of the circle, let me draw that first. There we go. And now I can come back, because of the way circles work, and draw a line that is perpendicular to that. So there you go. Now the green line is the tangent line. And the red line that's perpendicular to it is the what line? It's a secant line to the circle, but it's also the normal line at the point xy. It's perpendicular to the tangent line. You had this little theorem in geometry that said any line that passes through the center of the circle is orthogonal or perpendicular to the tangent line. That's one of the properties from Euclidean geometry. So this is a right angle right here. So I can find the slope of the normal line because I have 2 points, don't I? 0, 0, and x comma y. So that's going to be y minus 0 over x minus 0, which is y over x. That's the slope of the normal line. Well, I know the green line is the tangent line, so I'll call that m sub t, also known as dy dx. And since it's a normal line to the tangent line is normal to the normal line, we know the slopes are opposite reciprocals of each other. And what's the opposite reciprocal of positive y over x? Negative x over y. And that's a pretty nifty way to get the derivative without using calculus. But once again, it is the same as the calculus version. When there's more than one way to do something, they're both going to have to be correct. Otherwise, it's not a valid method. And so it's kind of interesting that we can arrive at it without even using calculus. It's like the substructure that we don't even see, that the mathematical ether allows these things to communicate behind our back. Wow. Long before we were here and long after we're gone. Interesting. Okay. Any other comments then on example 7? Are you always going to recognize what the graph of that thing looks like? Are you always going to have Wolfram Alpha to sketch them? No. So let's look at example 8. This is a rotated ellipse. Ellipses are a part of the conic sections, which maybe you had in Algebra 2. They are now a pre-cal obligation to cover those. But this is a rotated ellipse, and you don't have to know that because I gave you the equation. What we're interested in is part A. Determine the x values of any horizontal tangent line to that graph. All right, let me pick a flavor here. Green works. A horizontal line. Let me draw a horizontal line, snap it to horizontal, and I'll copy that one, and I'll paste it. It looks like I'm going to have a horizontal tangent line down there, and it looks like there's another horizontal tangent line about right there, somewhere in there. So it said not to find the coordinates. It said just to find the x values. So I want to know this x value right here and this x value right here. What type of symmetry does this graph have? It doesn't have y-axis or x-axis. It has origin, rotational symmetry. So those x values should be opposites of each other. Whatever their magnitude is, one's plus, one's minus. But they are kind of set off from x equals 0 a little bit. I guess after lunch, we're going to have to wait and figure those out. Okay, have a great lunch.